Here we go. All right. Come on. There we go. Thinking it's darn time. There it is. Tuesday is today. Wishful thinking. All right. We are going to continue our discussion on covalent bonds. Talk some more about the octet rule and how that applies to molecules. Look at multiple bonds that happen and talk about how to do Lewis dot drawings. So you're going to have 4 of those to do, and Ed has a video for tomorrow's asynchronous learning experience, because tomorrow we have a 5-day week this week, so tomorrow is nobody on campus. So what else? Page 216 was homework last night. I'll go over that before we get rolling and see if there's any questions on it. I'm guessing there probably aren't because it wasn't terribly hard, but I don't want to assume anything because that people are dangerous. So number 1 from the homework, how are the melting points and boiling points of molecular compounds usually different from ionic, and they're usually lower melting points and lower boiling points. What information does the molecular formula provide that tells you what kinds of atoms, what elements, and how many of each, right? H2O, hydrogen and oxygen, 2 hydrogens, no subscript on the O, so 1 oxygen. The only elements that exist in nature uncombined, those are, of course, the noble gases, as you know, and they are what we call monatomic as opposed to diatomic. How does a molecule that's NO, nitrogen with oxygen, differ from N2O? We're going to find out. Non-metals do some crazy things, and so it's not just simple. This is the ion, this is the other ion, crisscross it. They can combine in multiple ways, and nitrogen and oxygen are crazy. So NO has 1 of each, 1 nitrogen atom, 1 oxygen atom. N2O, just like H2O, and there's 2 nitrogens with 1 oxygen. And a diatomic molecule found in the Earth's atmosphere, well, there's 2. Nitrogen, which we'll be talking, and oxygen, we'll be talking about both of them today, and how they bond, which is kind of different. And then what information does a molecule's molecular structure give you? It gives you the connectivity, which atoms are bonded to which ones. When I say H2O, the 2 hydrogens aren't stuck to each other. Okay? The molecular formula or chemical formula tells you just how many of each. The molecular structural formula tells you who's bonded to whom. So that makes a difference. And there's often a little clue on shape as well. But we'll get into shape later. Oh, and Logan's here too. Yay, everybody's here. Good. All right. Any questions on the homework? Beautiful. So don't be bashful. If you have a question, let me know, but it's pretty much out of your notes. This is a panorama from Perseverance. Thought I'd share that with you. Colored panorama picture. NASA posted yesterday. Pretty apparent crater. Okay, so you can see the divot, and looks like they just landed just perfectly on target, and very cool, very desolate, nothing much out there. And the landing, let's see if I got this. Oh, that's a longer one. How interesting. Well, I have the really short one. That's all I'll do. You can look around and see the ones from other sources. I'm just going with the one from NASA. So they posted this yesterday.
Perseverance has slowed to subsonic speeds and the heat chill has been separated. Skycam maneuver has started. About 20 meters off the surface. We're getting signals from MRO. Tango Delta. Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
So silly when I get goosebumps. Anyway, makes me happy. So there's other videos out there, but I just want to share those with you. Color pictures of the landing is crazy. And of course, Tango, Delta, those are the abbreviations for the letters in the military. So TV for touchdown. All right. I heard somebody bloop. Let's see what I got going here. Bloop. I agree, Joshua. It's pretty stinking amazing and so clear. The images are so clear. Well, you would hope they have a good camera. All right. So in classwork yesterday, you got a note sheet. We got to here talking about how knowing the shape of molecules is important. We're going to talk about the octet rule, lone pairs, drawing diagrams, and double and triple bonds. You also should have gotten this. So I just wanted you to notice that all the steps, actually there's more steps on this paper than are in my PowerPoint. Oh, I just remember I forgot to talk about the honk rule. Okay, the fifth period. Anywho, so there's 8 steps on here. We won't get to doing the replacing the lines. I don't want you to do that yet. So just count up your dots. I've got them set into different groupings. I had hoped to get through all of set number 1, but I won't. I'll get through the first 3, I'm guessing, and then you'll have the last 4 to do the way I explain it at the end. And then as we go along, we'll work on these other ones. But for right now, let's take a few more notes, and then I'll explain how to do the Lewis diagrams, if that's all right. Alrighty, what's the result of electron sharing in covalent bonds? Everybody gets to be like a noble gas. That should sound super familiar. We've been trying to, elements try to get their s&p orbital, outermost s&p orbital electrons all full, whether they're making ions to do that or sharing. Remember, with ionic bonds, one has to lose when the other one gains. In covalent bonds, they share them back and forth, like co-workers share the workload. Okay, because the electrons are moving freely and rapidly, they're moving back and forth between both of the atoms and not hanging out by one. It's a really hard concept to get because when you're drawing these things, the electrons stay on your paper and don't move around. But in real life, they're moving all over the place. Again, the best that hydrogen can do, since it only has one valence electron and shares with another atom one valence electron, the best that it can do is get the configuration of helium, which is 2 valence electrons, but it's still a noble gas configuration. Right? So it's either a duet, right, 2, or an octet, and octet is 8. Hydrogen and oxygen are going to bond to make a water molecule, and in doing so, they share valence electrons. Oxygen has 6 valence electrons, that 2 of which need a buddy. Hydrogen has 1 valence electron, and so it's missing a buddy as well. But if those hydrogens sidle on up to the oxygen, then we get ourselves a water molecule. So this coefficient is, instead of writing H plus H, and then the oxygen, and these unpaired electrons aren't allowed to stay that way. They have to form a covalent bond or steal electrons from another atom, a metal. So in doing that, oxygen's going to end up, this is a dot diagram, right? And this is a structural formula which shows the bond, this shared pair of electrons as a straight line. Oxygen will have 6 plus 1 plus 1 makes 8, and each hydrogen is 1 plus 1 makes 2, like helium. So the shape of the water molecule, we'll get into that in just a minute. And that's because we've got to talk about lone pairs again. I've brought this topic up already, and I'm going to keep hammering it because it's so important to understand the shape of a molecule and how lone pairs affect molecules and how that affects physical and chemical properties. So our book calls them unshared pairs. Some books call them non-bonding pairs. Lone pairs are a lot easier. Group 5A or 15, that's nitrogen's family, has 5 valence electrons. And so when we do our little 1, 2, 3, 4, spread them out as far as possible, we have to start doubling up with 5. So that's a lone pair, and that influences the shape of molecules that have nitrogen in them. Group 6, which of course is oxygen's family, 6A or 16, have 6 valence electrons, 2, 3, 4, 5, 6. So the silly saying is they have 2 lone pairs. Lone pairs are a little extra negative. Okay, they are they have more of a force field, is one way to think about it. I know I've done this already with you, but I'm going to do it again. Ammonia is a super important molecule for mankind. We'll get into the process where people figured out how to split nitrogen molecules in the atmosphere to make ammonia. Originally, they did that for evil purposes, but now it's the basis of, ironically, fertilizer and keeping humans alive. It's just kind of ironical. All right, so nitrogen, 5 valence electrons. Each hydrogen has 1. Each of these unpaired electrons need a buddy. And yesterday I showed you this. This is, again, the dot diagram for ammonia, NH3. It has, on paper, the appearance of a T shape. It is not T-shaped. That lone pair on the nitrogen exerts extra pressure on the 3 hydrogens and pushes them out of the plane a little bit. What does that have to do with water? Well, water is a super tiny molecule. It's oxygen and 2 hydrogens. And you know, of course, that water is a liquid at room temperature. Each hydrogen is about 1 gram per mole, oxygen 16 grams per mole, for a grand total of 18 grams per mole of water. Okay? And we'll get into this a lot more soon. Other substances that you're familiar with, like nitrogen, is a gas. It's in the atmosphere. Each nitrogen's 14, so that's 28 grams per mole. Oxygen gas in our atmosphere, 16 times 2, 32 grams per mole. Carbon dioxide, 12 and 32, 44 grams per mole. I don't remember that from the mole-based stuff that we did back last semester, but carbon dioxide is twice as massive, more than twice as massive as water, and yet CO2 is a gas, but water is a liquid. Why? If it's so light, it should be able to be held up as a gas. And then you look at the noble gases, and holy cow, there's argon at almost 40, krypton's a gas at 84 grams per mole, xenon's a gas at 131 grams per mole. How is that possible? Well, it turns out the reason why water is a liquid is because it's sticky. And the reason why it's sticky is because it has two lone pairs. Those two lone pairs exert extra repulsion, okay? And I'm going to draw them on here. Those two lone pairs push the hydrogens away, and this is kind of a negative side to the molecule. The hydrogen side is kind of a positive side. Even though the whole molecule is neutral, keep that in mind, it's not got a charge. Just a little more, excuse me, a little more negative on one end and a little more positive on the other. Turns out that makes water molecules stick to each other. And so we're going to play around with some activities that will demonstrate that pretty dramatically. It is the reason why water beads up on a waxed surface, like your car paint if you wax it, or a mirror or something like that. The beading up of water and the way it can stick. Some of you have probably seen you could overfill a glass of water. You've probably seen that little parlor trick before. So water is a very sticky molecule because of these two lone pairs, and that's what gives it its unique properties. Super important molecule. Of course, you know that for your life. And you know that that's also, or you may not know, now you do, will, cation ions, when ionic compounds go into water, the positive gets attracted to the negative side of a water molecule, and the negative anions will get attracted to the positive side of a different water molecule. That's what allows them to dissociate in water. A little solution chemistry, a little early. Okay, so two lone pairs. Also, one other thing I just want to mention real quick. This isn't bad, how this is drawn. Water is what we call a bent shape, and we're going to go into that in great detail. Water is not a linear molecule, so please do not draw water molecules like this. Okay, it's not a line, just like ammonia is not a T. Okay, and we'll talk about that in more detail some other day. Methane's the smallest hydrocarbon. Simplest, it has one carbon, and then remember each carbon has 4 valence electrons that need a buddy. So hydrogen comes in and sticks to it. And this is methane, which of course is a greenhouse gas. It's cow farts and burps and all that kind of stuff. But there's no lone pairs. It's a gas and it stays a gas. It's not going to, you can't make this solid. And I'm not even sure you can liquefy it. We can liquefy propane under tremendous pressure. Okay, and so propane wants to be a gas. In between these, excuse me, is ethane. So if you live down in the valley, your natural gas is mostly methane, but some ethane gets in there. Up here in the foothills where it's a pain to drill, dig ditches, if anybody's done that, in granite, it doesn't work really well. Also, our population density is really low, and we're all spread out, so it's not cost effective to lay natural gas pipelines. That's why if you have gas at your house, you have propane. It can be pressurized. It can be put into canisters for your barbecue, for your camping stove, or for your house. Okay? So, but that's a pretty good sized molecule, right? 3 times 12 is 36, plus 8 is 44 also. So it wants to be a gas because there's no, it doesn't stick at all. There's no lone pairs. If you drew the structure, the dot diagram, remember the dots because it has dots, and a structural picture would just have lines. Again, each of those lines have 1 electron from carbon, 1 from hydrogen, 1 from carbon, 1 from hydrogen, 1 from carbon, 1 from hydrogen. Okay, they are single covalent bonds sharing 1 pair of electrons and no leftovers. If you don't remember your dots, I reposted this so you have it. Again, we talked about briefly that group 4A or 14 carbons family has 4 valence electrons. Nitrogen's family, which has phosphorus, is 5. Sulfur, which is oxygen's family, has 6, and the halogens have 7. So that is available for you if you need it. Again, we're not making charged particles. They're sharing the electrons. Nobody's winning, stealing them away. Let's go into dot diagrams. And again, you don't have to write down all of these rules. They're spelled out for you in gory detail on this paper. So determine the numbers of atoms of each element in a chemical formula. When you're asked to do a dot diagram of a particular compound or molecule, you got to look at the chemical formula. So this one's CCl4, carbon, and 4 fluorines. Again, we don't write ClClCl. Just write this sub 4. Second step, you figure out how many dots, how many valence electrons each element is supposed to have. All the halogens have 7. And then you draw a representation of that. Okay. 1, 2, 3, 4. Remember, spread them out. And then all but 1 valence electron. And there's 4 of them. You don't have to draw all micropoles for the homework tonight. Next thing you do, and this is just to help you evaluate if you've got the right answer at the end, total them up. Okay? So 1 times 4, 4 times 7, 4 and 28 makes 32. When we're all done, I should have 32 dots. Again, we're using chemical symbols, the element symbols for representing atoms. The next step is a little bit difficult, especially for beginning students. It's hard to know which one you put in the middle. Where do you start? Right? I'm going to suggest to you that look for the singleton atoms. So for example, CCl4, carbon, there's only 1 of them, right? We don't write a 1 here, it's understood. Same kind of thing if you're doing H2O. Start with oxygen, the one that has 1. It's a good place to start. It may not always work, but that's a good beginning point. Keep in mind that hydrogen and the halogens will never, one of the few nevers I can say, will never be in the middle. Okay? So they only can bond 1 time, and so they're always going to be off on the side somewhere. Here's this little silly thing, the honk rule, H-O and C. Let me, before I forget it. This is funny because the word's funny, I guess. But hydrogen can bond 1 more time. Oxygen has 6 valence electrons. It can bond 2 more times. Nitrogen has 5 valence electrons, 3 unpaired. It can bond 3 times. Carbon has 4 valence electrons. It can bond 4 times. So if that helps you, just remember how many 1, 2, 3, 4. That's nice and easy in a row, and it's a silly kind of pseudo word. So maybe that helps you remember how many. All right, so since carbon is a singleton, I'm going to put it at the center, and then the next piece to this is to start putting in dots. Another suggestion that works is to visualize it as symmetrical as possible, as evenly distributed around the central atom as possible. Make it, for lack of a better word, make it pretty. Okay. All right, so add in your shared electrons. So I just rotated the images. So these are the 4 from carbon. And then each chlorine has 7. Make sure that you completely correct, it says octet, but just make sure that you've got the correct number of dots around each one, and that should give you an octet around each of them. So that's another way to double check. So 4 from carbon plus 1, 2, 3, 4 from the chlorines. Chlorine has 7, borrows 1 from carbon part of the time. So does this one. So does this one, so does this one. And then just double count, double check your dots, right? So 7, and one's 8, 8, 8. I got 32. I'm good. Okay. And hopefully that won't be too difficult for you to do. I'm going to talk to you about double and triple bonds, and then I'll show you your assignment. Another way that atoms that can bond more than once, so they have 2 or 3 or 4 unpaired valence electrons, is with either double bonds or triple bonds. So in a double bond, unsurprisingly, there's 2 pairs of electrons, and we can just represent it with 2 lines. With triple bonds, 3 from one, 3 from the other, and we can represent it as 3 lines. Okay? So again, a single bond is just 1 from one atom, 1 from the other, and we can draw that as 1 line. If you're doing a structural diagram, okay, if it's a dot diagram, you got to put the dots. All right, oxygen. Oxygen has 6. Right, 2 available bonding sites. The other oxygen and the oxygen you breathe also has 6 valence electrons. And when you put the unpaired electrons next to each other, voila, we have our single bond. We're not done yet though, and this is where I can't emphasize enough that electrons move. So this makes a bond. That's easy enough to see. You've got a pair between them. What people forget is when you draw them on paper, these dots don't move. Electrons are moving at the speed of light. They're zipping all over the place, and you have to move them. So if you don't like scratching things out, then you're going to need to get an eraser. So by moving those, moving those electrons, let me get this out of here too. You end up with a double bond, and the 6 electrons from this oxygen borrow 2 electrons from the other one to get their octet. These 6 borrow 2 from this one to get their octet, and everybody's a happy camper. So this is a little prettier. Again, these 2, most of you would figure out, make a bond. What you have to remember is these electrons can move. Okay, so again, this is a dot diagram. This is a structural. I'm not going to get too picky about double bonds, but these are the lone pairs. And you'll notice that they've rotated away from the double bond because they're repelled. Everybody's negative. They're trying to get away from each other in space. I don't care if you put them at an angle. That's not critical to me at all. I want you to be sure and remember to put them on the diagram, though. And again, 8 and 8. One, 2, 3, 4, 5, 6 plus 2. 1, 2, 3, 4, 5, 6 of its own plus 2 from this one. Just when you thought you're getting it, here's a tricky one, but it's really not that hard. Nitrogen. Remember, nitrogen and oxygen make up our atmosphere, most of it, and they have multiple bonds between each other. They're diatomic elements, but they have multiple bonds. So nitrogen has a triple bond, and hopefully you understand that's because it has 3 unpaired electrons. So how does this work? Well, again, 1 from one and 1 from another. That's easy to see. What's not so easy to see is these unpaired electrons are going to move. Okay? They move. And that makes another bond. And then these unpaired electrons also move and make the triple bond. Okay? And they're not here anymore. That's not there anymore. And so you end up with a nitrogen molecule. Breaking that triple bond was quite a feat. So again, lone pairs, they have both of them stacked on top. In reality, they're going to get away from each other as far as possible in your life. I'm not going to penalize you for not remembering that, but the best diagram representation would have the lone pairs on opposite sides of the molecule. Triple bond between 1, 2, 3, 4, 5, borrow 1, 2, 3, gives you 8 for each of them. And in the book, this is the list of diatomic molecules. They say having oxygen as a double bond is inadequate. I say it's good enough for us. Okay? If you get into bonding theory someday, worry about it. But for right now, just know that it's a double bond. So most of these do single bonds, nitrogen's a triple, oxygen's a double. We'll go through carbon dioxide tomorrow. So here's what you're going to work on for me. I'm going to try these first 3, see if I can get them all done in 7 minutes. I think I can. And then you're going to do these 4. So on the paper, they're horizontal. On my slideshow, the vertical, they're the same ones. What do I want you to do? Work your way through those diagramming rules. So first thing I want you to do is make a dot diagram for each element. Just one of each. Okay, so this is hydrogen, this is iodine. Hydrogen has 1 dot. It's an alkali metal family, even though it's not a metal. And iodine has 7 dots, just like all the halogens have. 1 unpaired electron, each of them. So the next thing I want you to do is total valence electrons for the molecule. Pretty easy. 1 times 1, 1 times 7, add them up. When you're all done, you should have 8 dots. Next thing, I want you to draw the diagram. A dot diagram. So you have to have your dots. So hydrogen, whoop, iodine, whoop, 1, 2, 3, 4, 5, 6, 7. Count your dots. 1, 2, 3, 4, 5, 8. Okay, we're good. And then number 4, I would like you to circle the duet or octet. Okay, how does this get that element double gas configuration? So circle the hydrogen with 2, circle the iodine with 8. So we have an overlapping, kind of like a Venn diagram. Okay, OF2, oxygen. 1, 2, 3, 4, 5, 6. Fluorine, also a halogen. 1, 2, 3, 4, 5, 6, 7. 1 times 6, 2 times 7. Pull them up. That should give you 20 dots when we're all done. Start with a singleton, oxygen. Put in the fluorines. Circle. And then circle up to make it obvious how they got their octet in this case. So oxygen has 6 of its own, borrows 1 from each fluorine. Fluorine has 7 of its own, borrows 1 from oxygen. So does this one. Okay, we'll do one more. So you're going to need to do this probably by hand. I don't know how you would do this typing, and upload a picture into the assignment. This is C2H6. So we've got 2 carbons, 2, 3, 4, and hydrogens. We've got 6 of them. So 2 times 4 and 6 times 1. And 8 and 6, of course, is 14. Oh, I didn't count, but you guys can count. So the 2 carbons have to be side by side because that's the only way that they can bond. Okay, hydrogens can only bond 1 time. So draw in your carbons. Right here is the single bond that connects the carbons. And then conveniently, there's 1, 2, 3, 4, 5, 6 that need a buddy. So in come hydrogens. And you just made ethane. Or I just made ethane. And then the last piece is to circle up and indicate how they got their noble gas configuration. And it's a little bit trickier here with carbons. So each carbon's going to borrow that pair in the middle. 1, 2, 3, 4, 5, 6, 7, 8. And then same for the other carbon. It's a little bit hard. Okay, so everybody's got their octet. Sorry, that looks kind of messy. You are to do these 4. And please do them, like I said, by hand. I think it will be the best, the easiest, honestly, for you. And then upload an image. Either on my Google Doc, it's probably easier to just upload an image on your own Google Doc. Whew. All right, questions. There must be somebody with a question out there.